Kaggle leaderboard. Do you guys have access to the private leaderboard now?
Now we do.
Now you do? Okay, so you know. So I guess there's no surprise. So I had to just update this because I realized I took a result from like 158 and it was out of date, so I had to take a screenshot. So Black Tornado got his first place in the public leaderboard. And it turns out that they're also first place in the private leaderboard. Is Black Tornado in the audience, in class? Stand up, take a bow. All right, let's give him a hand. All right, so very curious about how, what you guys did in the write-up, so very curious to see what you guys did. Just a couple other notes. So last year, it was not like this. So last year, the person who was on first place in the public leaderboard was not in first place in the private leaderboard. And in fact, did a noticeable amount of overfitting. So you notice that the numbers are a little bit different. Just due to random selection, the private leaderboard data set was a little bit easier than the public leaderboard data set, just due to randomness. These numbers tend to get closer as the data sets get bigger. This data set was a little bit small, so not overfitting was very important. So it just, I don't want to pick on anyone, but for example, if you ignore the first two people who did very well, everyone else did kind of the same, and now you see, sort of more or less what happened last year, which was, if this were the first place team in the public leaderboard, would not have been the first place team in the private leaderboard. And I'm really curious about what the top two teams did, so I guess I'll find out on Thursday.
Or right now.
Can you tell us?
Yeah. Or right now, yeah, maybe a one sentence description.
Oh, we went on. So basically, we noticed that the variance was really high, so we went on GovTrack and then farmed, got a lot more data.
From where?
GovTrack.
Okay, collected more data. So that wasn't actually the same data, right?
I don't
No, it was just.
I made sure at least the test data wasn't the same.
Yeah.
So
So it's you were regularizing with extra data. Thinking outside the box. No, this will get you a data science job when you decide to.
What about Yellow Yakuza?
Are we making fun of the names or?
No, I want to know what they did. Yeah, did the second place team do the same thing?
The second place team is the second. What?
I talked with them, they did the same thing. But just probably less data than
Okay, lesson learned for next year's Caltech competition. All right, so today, just a reminder, the short write-up is due on Thursday, just a brief documentation of what you did, what you tried. Today, we'll be talking about some recent applications. Again, nothing here is going to be covered in any exam or any homework or mini project. It's just some highlights of recent applications. I mentioned 3 applications at the end of last lecture. After sort of writing down everything and preparing for this lecture, I decided to restrict it to just 2, just in the interest of time. And these 2 applications are closely related to each other methodologically in an area called learning reductions, which I'll introduce throughout this lecture as well. Okay, so before I talk about the applications, let's talk about sequence prediction here, because everything we'll be talking about today is closely related to sequence prediction. So in sequence prediction, you're given a sequence of inputs, and you want to predict a sequence of outputs, right? This is sort of without sort of a lot of modeling assumptions. This is sort of the way we look at it. And in conditional random fields and HMMs as well, we sort of make these first order dependencies between adjacent tokens in the output sequence in this case. And then in the conditional random fields, we sort of create some feature vectors that describe the relationship between these 2 adjacent labels, or relationship between a label and an input token. And then our model is some linear function in this feature representation. This is conditional random fields. And with some variable renaming and reparameterization of this as a joint distribution, this is also hidden Markov models. Okay? So what are some limitations of conditional random fields as sort of the simplest version that we talked about in the previous lecture, previous week? Well, first of all, they're a linear model, right? So in order for them to work well, you have to trust that a linear function over whatever feature representation you're using will give you a good scoring function, or lead you to a good model. If you do not have a good feature representation, then this will not give you a good model. So thus far, we've talked about how, let's suppose we had a feature representation learn a linear model, and everything's good. The one main exception to that we've seen in class so far are decision trees, right? Decision trees can work with, near arbitrary input representations, learn near arbitrary nonlinear functions over those input representations, especially if you do random forest or some sort of ensemble. And so they do not enforce a linear model. Everything else we've talked about requires a linear model, and so do CRFs, at least the version that we saw last week. Secondly, they only model first order effects, right? They only model directly the dependencies between adjacent outputs. And as we talked, if we want to model sort of more higher order outputs, the computational problem becomes very complicated very quickly. And so that's one of the reasons. And so, but today we'll be talking about two applications where only modeling first order dependencies will tend to not give you the best performance. So these are the two main limitations of CRFs that recent applications sort of take a different approach to addressing. So the first application is an edge detection. So the idea is given an input, which is some representation of an image, usually the pixel by pixel RGB channels of this image. So X is an array. X is a length by width by three-dimensional array of data, right? And then the Y is an array of edges, so just a length by width array of binary values, 1 or 0 if you think it's an edge. Or at least this is the ground truth. You can make probabilistic predictions. Like I'm 80% sure it's an edge. Right? But this is the ground truth. So this is the goal. So this is what the training set looks like. You get a set of X's that look like this and a set of Y's that look like this. And the goal is to train a model that can map images to edges. Okay? So one thing you can think of is, okay, what if we treat this as a two-dimensional conditional random field? Okay? So what does a 2D conditional random field looks like? Well, it has one output label per pixel. So if this is a 400 by 300 image, you would have 1,200, a lot more than 1,200, 400 by 300 Y variables that you're predicting, right? So that would be a two-dimensional conditional random field. Right? We briefly talked about models that look like this at the end of the previous lecture last week. So this would be sort of one place where you could use it. And now each of these Y's would be either 1 or 0, depending on whether or not we think this pixel has an edge. Right? Why are we modeling dependencies between neighboring pixels? Well, if there's an edge on this pixel, there's likely an edge, right, between some number of the neighboring pixels, because edges are drawn in a sort of a smooth way, typically, right? Even the ones that don't look very smooth, they look smooth if you look at the pixel by pixel level, right? It's locally more or less linear or continuous. Okay, so if we wanted to use a two-dimensional conditional random field, ignoring the fact that predicting the most likely Y here is NP hard, ignoring that fact, if we wanted to, just ignore the computations with this model, is this a good model, period, right? So for example, is only modeling adjacent pixels good enough, right? You can easily imagine if the image was super high, if the image, it's okay, you're excused, you're on the way. But no more freebies. Okay. All right, so, where was I? Okay, yeah, so imagine if this image was super high resolution, like it was, 4,000 by 3,000, right? A local edge between these things, might not mean anything at all, right? It's just too local of a relationship, right? And so this might not be a good model. Furthermore, what are the features, right? A conditional field requires some feature representation so that you can have a linear scoring function in that feature representation. What are the features? Right? In many application domains, that's a really hard problem that you have to come up with on your own before you can apply these type of methods. So today, we'll be looking at two applications of learning reductions, and I'll talk a little bit more generally about learning reductions at the final one-third of this lecture. And the basic idea of learning reductions is we're going to convert complicated problems into simpler ones. And the reason why we want to do this is because for a simple problem, we can use a complicated model, right? So CRFs is a complicated model. It's a complicated problem, but a relatively simple model, right? It's a linear scoring function over edges, essentially, right? It's a relatively simple model of a complicated problem. You can easily imagine the flip side. We have a relatively simple problem, but a complicated model. What is a complicated model? Well, like a decision tree, for example, or a neural net, right? Can you imagine applying decision trees to something like this? And then afterwards, we're solving a simpler problem, which basically means I'm solving a subset of this whole problem, essentially. We have to recompose the predictions of the simpler, made for the simpler problems back into a prediction for the original complicated problem. This is what learning reductions are. So what are some properties, what are some observations we can make about this particular problem? Well, first of all, it seems like local patches really matter, right? So for example, the edges here really do seem to follow some sort of local contour, right? So if I were to model, try to make a prediction in this area, and I'm predicting that there's an edge right here, then intuitively our model should also use that fact and also keep predicting that this edge keeps going down like this, right? So local properties matter, right? And the relationship is very complex, right? The mapping from pixel values, RGB values to these edges is highly complicated, right? Like this somehow corresponds to an edge, whereas for this particular annotation by some human, this part does not correspond to an edge, right? So it's a highly complicated and quote-unquote non-linear relationship between whatever raw representation you have, which in the simplest case is just pixel values, to the function, right? So we want to use something like decision trees. Okay, so that sounds really hard, right? Decision trees in this type of model. Here's another property that we can exploit, and it's the fact that this type of problem has weak global properties. One of the advantages of using a conditional random field or hidden Markov model is that the entire model is connected, right? It's connected using one-step dependencies, but it's connected. So what predictions we make at the beginning of the sequence can in fact influence the prediction we make at the end of the sequence through these first-order dependencies. However, I claim, without sort of not formally or very rigorously, just intuitively, that the predictions that you make here have absolutely no dependency on the predictions you would make here, right? It's a fairly intuitive observation, right? And I could look at this area of the image and draw the edges over here, and look at this area of the image and draw the edges over here. And then really, if I were to change my prediction over here, really it would not influence how I would change my prediction over here, right? So the global properties of this prediction problem are minimal, possibly negligible. We're going to assume that it's negligible because the edge detection is somehow a sort of a local property. So you really want to model higher order dependencies, but you don't care about propagating those higher order dependencies throughout the entire prediction problem. Yeah.
How do we know that how much detail the ideal edge should have?
It's
for example,
you learn from so in this particular problem, you learn from a training set that's been annotated by humans. So a bunch of humans says this is the type of edges I would imagine from this image. And you just learn the statistical properties, some nonlinear properties, if you're using a decision tree, that learns this. If some other set of annotators drew the edges a different way, then you would learn those statistical properties.
I see. So if maybe in the left box there was more detail, you could say that probably there should be more detail in the right box.
Right, but that's a property of the model, not of the prediction, right? If the model thinks I should predict more detail, still, how I drew the edges over here does not depend on how I draw the edges over here, right? Whereas if you think about conditional random fields, I know that now does not follow now. So if I predict the noun, it influences what I predicted the next word, right? Here, it's like, well, if I want to predict more detail, I'll just predict more detail over here, and I'll predict more detail over here independently. Or if I want to predict less detail, I'll predict less detail over here, and I predict less detail over here independently. Right? How much do you want to predict? You can think of it as a property of the model. Conditional on the model being trained, the predictions more or less independent. Right, so no need to model a fully connected model. No need to use a fully connected model. So what's the most obvious thing that one could try? Well, a sliding window approach. Here's how a sliding window approach works. We're going to assume that we have a model that can predict very well for 16 by 16 patches, let's say. Right, just as an example, 16 by 16 is just an example. You could use other sizes as well. But let's say that all the local patterns that we care about modeling fall within some sort of 16 by 16 patch. So then we have a model that takes a look at this 16 by 16 patch, and then predicts this, slides it over, predicts this, slides it over, predicts this, right? And so when we make a prediction over this 16 by 16 patch, we ignore the rest of the image, but we model the 16 by 16 patch as well as possible, using whatever hard, arbitrary, complicated model we want. So that's the basic idea, right? This type of sliding window approach sort of fits with both of these assumptions. Strong local properties that are more than first order dependencies, and weak global properties. So we don't need to model cascading propagation of our predictions across the entire image. Okay, so what model should we use? I think the answer is pretty self-evident given that I've said decision trees about 500 times already. So we're going to use decision trees. And recall just, this is what a decision tree is for binary classifications. You saw this in lecture a couple weeks ago. We have a root node, we have internal nodes, we have leaf nodes. In binary decision trees, binary classification decision trees, the leaf nodes are 1 or 0, right? That's your prediction. And then every prediction is made by routing some feature attributes of some person or some input into binary queries until you get to a leaf node. So this is the simple decision tree that you guys probably also used in the Caltech competition in various forms. So now let's talk about structured decision trees that can predict 16 by 16 patches of edges. So how would we do that? Well, okay. In the same way, right? So when you train it, or mostly the same way, at a high level, there are lots of details that are different, but at a high level, every leaf node predicts a 16 by 16 edge matrix, right? How do you make that prediction? Well, the simplest thing you can do is, you take all the training 16 by 16 edge patches in their training set that sort of partition to this leaf node, and you predict the average. Right? That's one thing you can do. And in fact, I think that's more or less what people do. Okay, so given a structure of a tree, given a query set and structure of the tree induces a partitioning over data sets of 16 by 16 patches of images and edges, then making predictions is easy. We just predict the average of the training set that partitions into each leaf node. So what does that mean? That means prediction is very fast, right? You don't have to do these dynamic programming approaches. You just branch down your decision tree and you're done. And you slide your decision tree across the image, and then you average the results. And in fact, this part is embarrassingly parallel. So if you had a parallelization, you can actually do this in parallel over multiple patches simultaneously. Okay, so given a train tree, this is pretty straightforward. What is the splitting criterion? What is the query set? Right, this is what remains to be defined. So this is based off of this particular paper called Structured Random Forest or Fast Edge Detection, appeared in ICCV 2013. Piotr Dollar was actually a postdoc here at Caltech some years back, now Microsoft Research. So here is just some 16 by 16 image patches. So here are the labels, right? And intuitively, if we just for this example, if I developed a split that splitted these labels, 16 by 16 edge label matrices, into this split, it's good because these edge patterns look the same, look homogeneous, and these edge patterns look homogeneous. If I instead split these edge labels into these two partitions, it's intuitively bad because now each of these are not homogeneous, right? And so now we want a definition of information gain or some impurity measure, impurity reduction, right? That can somehow intuitively capture this property, right? Capture what we can easily see visually, right? So here is the way they did it. I'm describing a simplified version of what they did. What they did is slightly more complicated, but the high-level idea is the same. We're going to map each 16 by 16 patch of labels into a coordinate system. That's the first thing we're going to do. Okay? So what does that mean? What are the coordinates? The coordinates are actually just random pairs of pixels on these image patches, and asking if they belong to the same segment or not, right? So for example, for each coordinate, choose a pair of pixels randomly set the value of that coordinate to 1 if these pair of pixels belong to the same segment, 0 otherwise. Okay? So for the first coordinate, we picked a pair of random pair of pixels, this one and this one. And so for this image patch, label image patch, they belong to different segments, right? This guy belongs to this pixel belongs to this image patch, and this pixel belongs to this image patch. So we set the coordinate 1 to 0. Coordinate 2, we randomly pick these two pixels, and now they do belong to the same image patch. So we set that coordinate value to 1. Right, so at the beginning of the whole process, we pick a bunch of these coordinates, maybe 100, maybe 500 coordinates. Each one of these coordinates correspond to a random pair of pixels, pixel locations, and that's predetermined at the very beginning, right? Now what this means is that for every image label, 16 by 16, we can map that to a coordinate system of zeros and ones, depending on whether or not these pair of pixels in this image belong to the same region or not, which is something you can compute using the training labels. So now we've mapped, so now we don't have to deal with this sort of two-dimensional, hard to sort of mathematically write down representation into just a coordinate system, right? So we do this for each training example. And then we're going to cluster the training labels according to their coordinate system. So now, intuitively, two images have the same spatial partitioning, right? The edges go through the same part of the patch if their coordinates are similar, right? That's the intuition. And of course, we could exhaustively try all pairs of coordinates, but that's often too expensive. And so what they did is they just tried a random subset of these coordinates, right? Does that make sense? Any questions on that? Yeah.
So how to determine the size of the patch?
So that's a hyperparameter. So in their paper, that was a hyperparameter that they tuned. Yeah. It depends on it depends in part on the size of the image, right? If it's a high resolution image, you probably want larger patches. If it's a low resolution image, you probably want lower patches. Intuitively, I mean, this is not a formal statement. Intuitively, what you want to do is you want the patch to be large enough to capture sufficient local curvature, so that you can make accurate predictions. So after you create these coordinate systems, we're going to basically cluster these patches using their coordinates into k clusters. K could be 10, 20, 30, something like that. Yeah.
So how do they check if it's within the same segment?
So in the training label, because these edges, so I mean naively you could say, does there exist a path from one pixel to another pixel if I traverse the pixel by pixel grid? And if I have to cross an edge, then there exists no path. That's a really computationally expensive way to compute that, but that's one way that will suffice us. There are more efficient ways to do that. So, I mean, in general, this is like a reachability problem, right? If you think of this as a Manhattan grid of pixels, you want to ask, what are all pixels reachable by this pixel before I have to cross an edge? Now, all the ones that are reachable are in the same equivalence class, right? And then if any pair of pixels, if I select any pair of pixels within this equivalence class, they belong to the same region. Yeah.
Is it a big issue of like the quality edge classification? Because when I've seen edge classified things, like occasionally like little breaks or little things that and it seems like a 1 pixel break here would totally change this detection.
In the annotation?
Yeah, the annotation. Yeah.
Yes, it would.
So is that in practice, is that an issue, or is the annotation?
Well, certainly if there's an annotation error of that magnitude, it would break this.
Yeah, but it seems like the tiny little annotation error. So someone's doing with an Inkscape and they accidentally click twice.
It would certainly cause. I mean, you can see here that the edges are kind of smoothed a little bit, right?
Yeah.
So I don't think that. I mean, I'm not a computer vision expert. There are things they do to deal with these issues. I would imagine that they would deploy those things and do a little bit of smoothing of the annotation so that doesn't happen. Okay, so if we have this coordinate system and we use this coordinate system to cluster labels into k clusters, and k could be relatively large, like 100. Again, that's another tuning parameter. Then we've now reduced the problem into some notion of multi-class classification, right? We want, at least from from the information gain criterion, we've reduced it from this really high dimensional space down to just k clusters, right? And that's just multi-class entropy, right? Which is just a generalization of the binary class entropy that we looked at in lecture. Right? So now we don't look at the values, what's in these, what the edges are in these patches. We just look at their cluster memberships. Okay? And so in this simple example, there's only 2 clusters in this particular current internal node, which is the blue cluster and the red cluster. So all these image patches belong to the red cluster, orange cluster, and all these image patches belong to the blue cluster. So now impurity measures multi-class entropy, so we want to split that, we want the best split from our query set that splits the data into as pure subclusters, subpartitionings as possible, as defined by our cluster entropy.
So K is a hyperparameter here.
Yep. So when you deal with these types of methods, there's going to be a lot of hyperparameters in practice, and tuning them is a little bit of a pain, but I don't think it's too hard. Yeah. And so this is you can think of this as basically, if you're familiar with the terminology, we do random projections to define a low-dimensional coordinate system, and then we cluster under the assumption that it's a membership model from k underlying clusters. And given that once we infer the cluster memberships, we don't actually care about the original labels anymore. So it's a way of doing dimensionality reduction so that we can do a more reliable, lower dimensional measure of information gain or impurity reduction. Okay, so we've talked about how to make predictions. We've talked about what is the definition of information gain. So the last thing we need to specify is what is the query set. And after we specify all 3, we can train the tree and we can use the tree to make predictions. Okay? So what is the query set? So in their paper, they chose to, and this could be played around with a bit, but in their paper, they chose to use color gradient. So let me just give you a few examples. And the query set is huge. It's over 7,000. But here's just some examples, like the image gets darker from the first column to the 5th column, right? So this is the you compute the average pixel intensity of the color intensity of the first column. You compare it to the average color intensity of the 5th column. You ask if the average color intensity of the 5th column is lower. If yes, then you branch to the left. If no, you branch to the right. This is the notion of a color gradient. Or the image gets more blue from row 7 to row 3. So you compare the image at row 7, the average blueness. You compare the image at row 3, the average blueness. It's more blue in row 3, so you branch to the left. Otherwise, you branch to the right. You could just imagine it's a near exhaustive set of these types of queries, and that's your query set. So at test time, given a train tree, you take this image, you slide this window, you slide your sliding window across this image, and for each image patch, you issue it a bunch of queries. It branches on this image patch. It branches to a leaf node, and then you predict the average edge matrix of the training data that fell into that leaf node. Again, the actual approach they did is a little bit more complicated, but this is basically the level of it. Okay, so putting it all together, the first thing we need to do when we train this model is create a new training set, right? Because the predictor is designed to predict over 16 by 16 image patches, which is not what the original training set is. So it's a fairly straightforward construction of a new training set. We just take all 16 by 16 patches of all the original images, and we just lump that together to a single training set. So we just converted a training set of sort of variable size images into a larger training set where each individual instance is a 16 by 16 image. We train our structured decision tree on this modified training set using the query set that we just looked at on the previous slide and the structured information gain criterion from the slide before. And then of course you don't have to use decision trees, you can do random forests. right? You could subsample this, you could subsample the 7,000 queries in your query set, so you don't actually have to use decision trees. In fact, they use random forests. But that is just a straightforward modification of how decision trees are trained. And after you've done that, you predict by sliding this decision tree over the input image of some test input image, and then you average the predictions. That's the entire approach. How does this work? Here are some results, and these results, by the way, are very, very good. This is from their paper. So, for example, the projector is a little crappy for this. I apologize. This looks better on a monitor screen, on a laptop monitor. And the edges, I guess, are a little bit too fine. But anyways, there's two types of averaging going on here, right? First, the sliding window approach averages a bunch of predictions together, right? Because you do this overlapping sliding window. Second, you're using a random forest, not a single decision tree. So all their numbers are going to be, typically smoother. All their predictions are typically smoother versions of the ground truth, but they look very good, right? And then you can do some amount of post-processing to convert these edges into sort of more sharper, and that's what these results are. Yeah.
Where does that ground truth come
And it's
from?
annotated by some human annotators. It's a supervised learning task. So the training set includes, this is held out test set, but
Yeah, because I had the same question before. Segmentation or edge detection is often unsupervised. And I was wondering, where do these training examples come from? That human just has drawn all the edges carefully, or?
Yep.
Okay.
Computer vision is built on the back of human annotators. In fact, how to maximize the efficiency of human labelers is one of the most exciting subfields of computer vision. I'm not, okay, I guess that was kind of a joke, but not really, it was not a joke. It's serious, it's a serious endeavor.
So are human annotators better at edge detection in terms of like speed and accuracy?
It's a hard question to answer for this particular problem because we're trying to mimic the human annotators, right? The human annotators are considered ground truths by definition they're the best. Now in terms of accuracy, there's different ways to answer your question, right? So from a crowdsourcing, so the area is called crowdsourcing for those of you who are interested. In crowdsourcing, obviously there's a notion of ground truth, and a human expert, an expert annotator, is considered the ground truth often. In which case, whatever they say, you have to match, and 100% accuracy is doing what they do. Of course, many human annotators are not that good, right? They're novices or imperfect, and so you can measure sort of inter-annotator variability as one way to think about how good these annotations are. You can try to teach annotators to annotate better through certain small training tasks. So this is actually a very rich area of research. How to maximize the effectiveness of some sort of human-machine combination, which is getting humans to annotate these things in an efficient and accurate way. Yeah.
So it looks like the algorithm's doing a lot better than the ground truth, like just intuitively based on looking at it.
So it's a little bit of an artifact of this projector. This looks a lot better on your laptop.